Wir möchten gerne weitermachen. Nächster Vortrag, Elrifai von Pentau, Director für Enterprise Solutions, und er wird uns heute über seine Lieblingsthemen erzählen, IoT und Big Data Science. Wael, thank you for coming.
Thank you. As Stefan said, my name is Wael Elrifai. My title is Director of Enterprise Solutions at Pentaho. I don't know what that means any more than you do, but my background is basically artificial intelligence, machine learning, IoT, and things of that nature. So while I'm not going to show a demo today, I'm going to talk about a use case we've dealt with. I'm going to talk about a framework for approaching things in general. And I don't know, can I see a show of hands? Who here has dealt with machine learning? A couple of people. So a lot of times, you know, I only have 20 minutes, so we're not going to get much out of, we're not going to go into much depth. What I'm at least going to do is cover some of the main headline topics. What is supervised learning? What is unsupervised learning? What's the difference with stats? And how does Pentau fit into it all, okay? Now, as a company, we're dealing with a lot more IoT type solutions. Matt earlier presented some really interesting stuff, especially around streaming, and he talked about MQTT. It's a broker for sensor systems, right? As we see the market shifting this way, you know, we're going to have to start integrating into that ecosystem. And I'll be talking a little bit about that. But I want to start with something else. You know, why do we talk about big data? When we say big data, we mean distributed systems, right? We mean Hadoop. We mean things like that. Why do we talk about Why do we talk about that? Why is that important for dealing with IoT? Quite simply, the types of problems, the types of mathematical applications and things like that that you use with enormous data sets, time series data sets and so on, are the kind of algorithms that can be applied in parallel. So there are things that we call embarrassingly parallel and things that are not, right? So sorting, for instance, is not easy to parallelize. There's a method, we're not going to go through the detail. But other things parallelize very well, like matrix operations, like machine learning, which is why big data systems are so key in IoT. So let's start with a question we should be asking ourselves. One of the big problems I commonly see when I'm talking with execs in big companies is they don't ask a question, they start with what data do I have? What can I discover? In fact, you can see this when people talk about how to use their visualization tools. Oh, pull all your data in and see what correlations you can find. You're going about it backwards if you're doing that, right? What you should be doing instead is saying, what is the problem I want to solve? And what data would I need to solve it? So what could I do if I had perfect, universal, and timely information? So perfect, as in the data is of high quality. Universal, in other words, all the world of knowable data. Not necessarily what's in your organization, but what is the whole purpose of PDI? To incorporate data from a bunch of systems, right? They don't have to be from your system, they can be from anywhere. So universal, the universe of knowable information, and timely. Does that mean real time? No, I don't even know what real time means, to be honest with you. Does it mean 2 seconds, 1 second, a millionth of a second? I have no idea. It means in time to make your decision. If the reacting system is if the system on the other side of that real-time chain is a braking system on a car, then maybe it's a millionth of a second you need. But if it's a real-time trading platform, it's 1 millisecond. And if it's something else, it might be less, right? So timely as in time for your business. When we start with that, we can start talking about a framework for IoT. When we talk about IoT at Pentaho, we commonly talk about the 5 C's of IoT. What we mean here is connections. This is a smart connection. This is how we move data from the physical world into the cyber world. This is sensors and communication systems, right? That's not really part that we get involved in, right? Now our parent company Hitachi does some of that stuff, but we don't really do that. Then we talk about conversions. What I mean here is data to information. This is what we call in our marketing speak data blending, right? What we mean by data blending is, imagine you've got, I'll use this example later, but imagine you have a train and there's a sensor that says if the door is open, right? And it's saying door open, door open, door open, door open. That by itself means nothing, right? It's only meaningful in the context of knowing that the door has been ordered to be closed and how long ago the door was ordered to be closed. In that context, now it's meaningful. That's a data to information conversion. But it's not actionable, is it? It's just a piece of information. You went from data, now you have information with data blending. When I talk about centralization, I don't mean in the mainframe sense that it all needs to be sitting on one big server. What I mean is that the data can all talk to each other. So the common term we use here is data lake, right? Cognition. When I'm talking about cognition, this is where the machine learning piece comes in. Cognition is about being able to take that information and make something actionable. So cognition is about prediction. And then finally, CI. Continuous improvement is all about taking the actionable information from the cyber world and making it physical, feeding it back into the physical world. Now this can be done in an automated fashion. You could have a PDI system that writes to a machine system and actuate and runs actuators and run machines and whatnot, but we don't typically do that, and for a very good reason. Once you do that, you're in the realm of control theory, systems engineering, mechanical engineering, and so on. So we don't typically feed all the way back. We use these decision support systems. Yeah? Is everybody with me? Am I talking too fast? Talking a ridiculous accent? No? Okay. So some of you, there's too much laughing with that one. So one of the things we talk about here, those of you who've heard me talk before, I always talk about this case, Hitachi Rail. Hitachi Rail basically wanted to switch to a predictive maintenance platform. Whenever we talk about IoT, that sort of top use case that gets a lot of play right now is predictive maintenance, right? Then there's schedule optimization, total asset optimization, and basically down the list. That predictive maintenance case is important. Why? It's important when you're shifting from a CapEx model where I shove as many trains as you'll take down your throat, right? You just buy as many trains and I get the maximum CapEx, versus an OpEx model where you're buying train as a service, where I've got to deliver a certain amount of transport. Now in that world, I want to minimize the number of trains I use to deliver that service, don't I? So what I want to minimize is what we call unscheduled deferment. That's a fancy way of saying the train broke down. Yeah? So reducing maintenance costs is all about being able to predict when something's going to fail. Now this system has 3,000 sensors on it. Each of those sensors operates at 5 hertz, and there's 241 trains in the first phase. So you have on the order of 3.6, 3.7 million data points per second, around 110 trillion, I think, per year. So it's a pretty big data set. But the kind of problems we want to solve are highly parallelizable. Perfect for big data platforms, perfect for PDI. Perfect for PDI here. So what we want to do, those use cases we hear about are anything as a service, outcome-based pricing, usage-based pricing, PDM, schedule optimization, total asset optimization, and then the more technical use cases we hear about Internet of Things and big data science. So we use some other terms for this, right? We use industrial Internet of Things, and then originating here in Germany, there's another term we commonly use. Anyone know? Industry 4.0? So does that make sense? Am I talking about something that makes sense here? Kind of. No, not really. Everyone's had their fill of cake and is asleep. All right. So we're going to talk quickly here. How am I like on time here? I'm okay? All right. So let's talk about, I'm going to do a very, very rough outline of predictive here. What do I mean when I say predictive? Now, I've broken it down to 4 blocks here. These 4 blocks are not mutually exclusive. Anyone who's familiar with machine learning knows plain old statistics is featured in all 3 of these other ones. And even the lines between reinforcement learning and supervised learning are blurred. But this is useful for an entry-level discussion, all right? Sorry, I'm losing my voice a little bit here. So, quickly, when I say plain old stats, what am I talking about? I'm talking about ordinary least squares, Gauss-Markov distributions, and things like that. We're not going to bother with that at all now. I'm not going to show any formulas. Reinforcement learning. Reinforcement learning, anyone here has heard of AlphaGo? Come on, from Google? Yeah, the Go playing computer. How did that system work? That system learned from interacting with its environment. Everyone here knows the concept of A/B testing, right? You've heard it especially in website usage. Imagine you have a system that runs experiments, but the problem is when there's a website layout, let's say it's eBay or Amazon, there's a million ways they could lay out that website. There's a million colors they could use. And in fact, there are variations outside. Maybe stickiness of the website's different when the weather's like this versus when it's blue outside, right? So they want to run all these experiments against all these variables. And in fact, when you expand it out, it's trillions of experiments. Can they run all trillion experiments? Not feasibly. So they need a method to boil that down to the core experiments that really cut to the heart of the matter and allow you to separate the wheat from the chaff, figure out what's important. That's what reinforcement learning is all about. I'm not going to talk about either of those more than I just have. I'm going to talk quickly about unsupervised and supervised learning. So let's talk about, at a broad level, unsupervised learning. What we mean by that is that we don't have targets. We don't know the label data. We don't know the outcome. So what is a target if I'm building a predictive maintenance system? Did it fail or not? That's a target. Or maybe total output of the engine. That's a target, an outcome. Yeah? So the input data is the sensor data. It's the data from the ERP. It's the data from the weather. It's all that stuff. The outcome data is output of the engine or binary. Did it fail? Did it not fail? So when I don't have that data, on day one, when I roll those trains onto the tracks, do I have outcome data? No. No. So the best I can hope to do is to predict anomalies. Predict if something is predict if something is doing something new. Is the system operating in a new way? Yeah? That's what you do with unsupervised learning. With supervised learning, it's actually, now over time, we've started to have failures. And really with machine learning, what you're trying to do is, this is the input data, this is the outcome data, and this is the black box in the middle. I want to tell it to apply a certain algorithm, a certain approach, and find a way to tie those two together. If I don't have that outcome data, well then it's unsupervised learning. Who here has heard of k-means clustering? If you've heard of machine learning, you've heard of k-means clustering, right? You've always heard of the anomaly detection, k-means clustering. There's a few applications for this, but here you can see a very simple 6-panel application of k-means. What k-means is all about is you tell the system how many clusters you want to put the data in. That's the k, right? That's called a hyperparameter, by the way, just so we're fluent on the technology terms. We tell it, I want to find me the 4 smallest circles, put these 4 little stars in a place on the panel such that I can draw the 4 smallest circles, such the sum of the areas of the circles is minimized and still captures every single data point. Can you see why that's useful? It basically finds underlying structure in the data. Yeah? So you might find there are 4 modes of operation. Now, in this case, would you actually apply a machine learning algorithm to this problem? This is evolution over time, panel 1, 2, 3, 4, 5, 6. Would you actually apply a machine learning algorithm in this problem? There's like 50 data points in 4 clusters. I can see this visually, right? Would you bother? No. But imagine we had 3,000 sensors. How would you visualize 3,000 dimensions? Impossible. Not 3,000 data points, 3,000 dimensions. That's where we start talking about machine learning. Now the system basically what it's doing is it has a heuristic called gradient descent. So that it knows how to move the stars in roughly the right direction using some experimentation such that by the end of it, it hopes to have found the 4 optimized clusters. You can see the stars are moving in each panel, right? Does it look like it did a good job at the end? At the end of panel 6? Would you say yes or no? Well, in this case, it looks like it screwed up to me, right? It sees 2 clusters up here, 1 down here, and 1 here. That's probably not right, right? The point is, the heuristics are generally good. Generally. They're not perfect, and usually you run many tests. You do what's called Monte Carlo analysis, right? You run many experiments. It's based on a heuristic. Because the problem is what we call in mathematics non-deterministic polynomial time complete, or hard. It cannot be solved. If you have all the compute power available from now until the end of the universe, you could not solve the problem for sure, right? So what you do is you use heuristics, the same way your brain works. You know, I was speaking at an event last week in Dusseldorf, at an antique car showroom. It was pretty awesome. And there were all these sports cars there, and I was talking about this. Now, As I walked around the showroom, there was an old Ferrari there. I noticed the color of the interior. I noticed the make of the car, the year, and so on. However, if that same car had been coming at me at 200 miles an hour on the road, would I have noticed the color of the interior? Probably not. Why? Because my brain has a heuristic. It skips all that and it goes right to the problem to be solved. This is the same thing. With this gradient descent algorithm, skips all the noise and goes to the problem to be solved. In this case, it didn't work. But in general, it works, right? That's what machine learning is all about, heuristics. When the problem is too complex to solve through brute force, you apply machine learning. So when you have a problem that can be solved by brute force, should you apply machine learning? No, it's a silly approach. Let's say it's supervised. In a supervised learning model, we have the outcome. In other words, we know if we operate over time like this, the train fails in this way. It might be time series data, right? So it's really two-phase. In phase one, we train the model. So the blue ones, this process of going from raw data and creating feature vectors to build your algorithm, what tool might you use for this? Can you think of any? Come on, honestly. For shame. Pentaho data integration, right? This is a data engineering task, right? You're creating feature vectors is a fancy way of saying structured data. When we talk about dealing with structured and unstructured data, do we ever do things with unstructured data directly? No, we apply structure. In one way or another, we apply structure, right? So PDI is all about that, being able to blend the structured and unstructured data. And that's what big data is all about. That's what Hadoop is all about. So here, this is allowing the data engineer, the data scientist, to take the heavy lifting. If you're using Python, what are you using to do data engineering? You're using pandas, right? Pandas or something like that. All that data engineering takes a long time. Do it in PDI, it's quick. So PDI allows you to build that. The labels are the outcomes, the targets, right? You tie those together with an algorithm, a black box. Now, the green part is deploying that algorithm in real time. But guess what? The best algorithm that you built here, the final version of the data integration code that you wrote here, it's almost perfectly reusable in the online version. Because after you finish training the system with the perfect features, well, that's the same transformation you want to do the incoming new features, isn't it? In the online system to make predictions. So you take that code, you remove the label data, and you put it here. You take that model you built and you drop it into PDI. If you've ever seen the data science pack in PDI, you'll see that it's there. The capability of dropping Python, reading from data frames, R or Weka, yeah? And now you can make predictions. And what are some of the algorithms used here in supervised learning? Anyone familiar with any of them? So in time series, well, so some of the ones you might be familiar with are support vector machines. You might have seen those shirts, joke shirts, I support vector machines. No? No. All right. I feel sad. No, the other one is a very common one when you're dealing with time series data, what's called data where the future data is based on what happened in the past. In other words, data that's not entirely stochastic, data that's a Markov chain. These are the terms. I'm not saying them because you need to know all this. I'm saying them so you're familiar with these terms in general. So when you're applying that, if you have a Markov chain, data that's stochastic in that way, a common approach is artificial neural networks. You must have heard of that. Okay, you definitely heard deep learning. That's a type of artificial neural network with many layers, right? And commonly, if you're doing over time, an approach you might use is LSTM, long short-term memory, or recurrent neural networks. Again, I'm just throwing terms out there so you're comfortable hearing them. We're not going to go through the math, I promise. So in PDI, this is one we put together for Wael. We're taking in data on how basically this is data about failures. We're taking in all that data, we're doing all that data engineering, and we were building what's called the a priori algorithm. It's an algorithm to figure out what are the most common joint probability distributions for failures. Because you know what, failures aren't just about the, aren't just, it's not just about the trains. It's also about the location, right? It's not just about the location, it's also about the time of day and the weather and so on. It's called a joint conditional probability. So this is all about data engineering, and this was all about the algorithm. When we're done and we want to make predictions in real time, we deploy this online. And now we have outcome data coming out of the whole thing. And now what we discovered here, this was with Network Rail in the UK, we found out that there were all sorts of problems they had no sense of. And in fact, we found out that most of the problems come down to running a certain type of train through a certain type of crossover point. If you don't run that particular train, if you run any other type of train through that crossover point, everything's fine. But that particular type of train, which through that crossover point, is causing like 20% of the system failures. Because it's not just about that train breaks. What happens when a train predictive maintenance is very different than a car predictive maintenance. Because when a car breaks, what happens? Well, you turn it off, pull by the side of the road, and you call AA, right? What happens when a train breaks? A multi-million-dollar asset is offline, and a section of track is offline, and potentially a platform is offline. Maybe a multi-billion-dollar asset, right? So it's a very different use case. Toolkit, quickly, 30 seconds. Data capture systems. This is that first C, right? Smart connection. Communications platform, moving the data over the network. Data storage and computation. So if you're doing computation, it might be something like it might be Pentao's engine, data integration engine, or it might be something like MapReduce, or Spark, or Flink, and so on. Machine learning and evolutionary algorithms. I haven't talked about evolutionary algorithms at all, but genetic algorithms, gray-coded algorithms, things that mimic biological system evolution. GUI-based abstraction tools. Can anybody guess what I'm talking about here? Right? Graphical user interfaces. This is a business layer abstraction, which is what PDI is all about, right? Creating abstraction layers so that you don't deal with the underlying. Why would you guys want to deal with what's happening underneath? And I've got to add this one in there. Don't be fooled by visualizations. I know this is just, everybody loves visualizations, Tableau and Click, and everybody loves MapViz, right? Whenever you see a map, it's cool. But how many data points can be in a single section of a map? Well, the location. Maybe the size represents people. Maybe the color represents political affiliation. Maybe you can fit one or two more methods, cross-hatching or something. It's like 4 or 5 data points, right? Per area. How many real-world phenomena are limited to 5 data points? None. How would you visualize 3,000 dimensions? Impossible. So visualizations, I know that viz companies talk about how you can use it to explore your data and figure out correlations. No, you cannot. You cannot. Visualizations are when you want to show management what you already solved. You want to put a report, an operational report, to explain what's already been done. That's what a visualization is good for. So, because human beings, we're really good at detecting patterns. You can tell a loved one but when you see them by the back of the head, right? You can tell a loved one by the way they walk. We're so good at pattern detection that we're primed for it. If I give you a primer to detect a certain pattern, you're going to see it. So I'm going to leave you with this. Drunk octopus wants to fight. That's a coat hanger. But does anybody see a drunk octopus here? I absolutely do, right? In fact, I saw this for the first time like 2 years ago. I can't look at a coat hanger in my home anymore without thinking drunk octopus wants to fight now. And now you too. All right, with that, any questions? There's probably no time left because somebody's hovering over me.
Thank you.
Thank you, guys.